Hello, welcome back. The title of this lesson is called Angular Speed and Rotational Speed. This is part 1. So we now know what radians are. We know what radian measure is. And now we need to transition from just talking about static objects to objects that rotate. I don't think I need to convince you too much to understand how important that is. Anything with a rotating aspect to it is going to be using the ideas in this lesson. So when you think about even the wheels on a train going around, or the wheels on a car, or internally into the engine, you have rotating pieces. Inside of a rocket engine, you have rotating pieces of the rocket motor on the inside of there. So anything that rotates, we're going to talk about angular speed. So let me first draw a couple of angles on the board, but in the back of your mind, as you watch me draw these pictures, I want you to remember that angular speed is just measuring essentially one way of taking a look at how fast something is rotating. That's what it basically is. So let's draw a rotating situation at 2 points in time. So let me go ahead and do that. Let me draw one circle, initial point in time, and then we're going to draw another circle, which is, I don't know, some small time, a few seconds into the future. So I'm going to draw a little dotted line, which would be like an XY axis, which cuts through here like this. You could say this is X, this is Y. We have a little situation like here. Here's X, and everything, for a unit circle or whatever, you can think of it superimposed on an XY axis like this. So let's take a look at initial position. So I'll call this initial. Initial. So what we have is from the center of the circle, as measured to the edge of the circle, at some radius r, and it makes some angle, I'll call it theta sub 1 with the x-axis. All I'm doing is saying this ray, we have to measure its position somehow. We're calling it a distance r, which just means a radius of the circle, right? And as we sweep around, the radius of the circle stays the same. So how do we measure its position? We measure it as an angle to the positive x-axis. So the initial position of this ray in this position is measured theta sub 1 radians from the x-axis. Could be 10 degrees if you're working in degrees, or it could be more appropriately expressed in radians, some radian measure from the x-axis. Now what's going to happen is we're going to allow some time to elapse, all right? And so we're going to say later. How much later? Well, it depends on how fast this thing is rotating. We can consider it to be like 5 seconds later or whatever. So initially, you can, the initial position I'll draw there and kind of superimpose on there. But really, I'm mostly interested in drawing the final position of this thing, which will be like up here, right? Now again, it has some radius r, and the position of this ray is always measured with respect to the positive x-axis. So really, it's measured down here, like this. We'll call it theta sub 2. So this dotted blue line is just there for reference, okay? It doesn't have anything to do really with the final position, which is here. It has some new angle, again, measured with respect to the x-axis. So you can see that initially it had a small angle. Some seconds later, it has a larger angle. We just call it theta sub 2. Now, as this thing rotates from here to here, initially it was in this position, and then it moved to this position. So as it rotates from the initial to the final position, we say the end of the thing sweeps out in some arc length from here to here. Because initially it was here, and then it goes here. And so if you could add up all the distances the tip of the thing traveled, it would be some arc length, which we've already talked about arc length in the last lesson. So if we wanted to figure out, remember where we're going with this is trying to figure out how fast things rotate in terms of the angle, the angular speed. So I'm not talking about meters per second, that's just a straight line speed. I'm talking about angular speed. How many radians does this thing sweep out per second? If it's a very high number of radians per second, let's say it's like 2 pi radians per second. Remember, 2 pi is all the way around the circle. So 2 pi radians per second would mean all the way around the circle in 1 second. 1 second, 1 second, 1 second. And of course, it doesn't stop. So 2 pi radians per second would be sweeping out one circle every single second, right? Now, what if it were like, I don't know, half of that rate? So it was half of that original rate. Well, then it's going to be sweeping out half of the angular speed, where the angle is what you're measuring here. So if we start at angle theta 1 and we end up at theta angle 2, what is the difference in the angle? We can call it a delta angle, the difference in the angle between state 1 and state 2. So what we can do is we can write down, is we can say that delta theta, which is just the difference in the angle, is theta 2 minus theta 1. So if we start out, at some small angle and end up at some larger angle, we subtract the angles, and that's going to measure the difference in the angle from the starting position here at the dotted line to the final position here. When we subtract these two things, we're going to get the delta angle that is swept out from the starting position to the final position. All right, and that's what it is. It's just a subtraction. So let's just say that this sweeping out of this angle takes, whoops, if I can spell take correctly, takes t seconds. So let's say that we sweep out from position 1 to position 2 in however many seconds it takes. We call it t seconds. Then what we can say is that we can define what we call an angular speed. Angular speed. And we call angular speed lowercase Greek omega, which is like a W, but it's like a curly W, right? I know that it looks a little weird, but a regular W is like this. That is not omega. Omega, lowercase omega, is a curly W like this. Capital omega, you've probably seen, is this. This is a capital Greek letter omega. This is a lowercase Greek omega. We use omega, lowercase omega, almost all the time for angular frequency. It is a Greek letter that you will use forever in physics, electrical engineering, mechanical engineering, aerospace engineering, mathematics. You don't use it so much in chemistry because we don't talk about angles too much in chemistry, although we do for angular bonds, angles between bonds in chemical molecules, right? Or in molecules. But this is the way you want to draw it. You want to draw it with a nice kind of a rounded bottom, essentially. I'm trying to say it nicely, but a rounded bottom. That's the way you want to draw it. That is lowercase omega. And what it is the angle that you swept through from the initial to the final state, and you divide it by however many seconds that took. And what you get for a unit is radians per second, because on the top, when you subtract the angles, what you're doing when you say theta 2 minus theta 1, you're figuring out how many radians did you rotate through. So the unit is radians, and how many seconds did it take? So how many radians per second did you sweep out? If the number that you get is 2 pi radians per second, then that means one revolution of the entire circle, because 2 pi radians is the whole entire circle per second. So that's kind of like your baseline. 2 pi radians per second is all the way around every single second, okay? Any other number of radians per second is going to be slower or faster than that. So it's specifying a rate, but not a rate in terms of distance. Distance of traveling in a straight line is like meters per second. That's just a linear distance. This is measuring how fast something is rotating by characterizing how much of an angle you're sweeping out every single second, where the angle is represented in radians. All right, so lowercase omega right here. All right, and we call this angular speed. We don't just call it speed, because when we say speed, we always think of meters per second. Angular speed is literally what it says. How fast does the angle change? All right, so that's the angular speed. And then what we can do is we can kind of translate this, and we can talk about what happens on the edge of the circle. So let's go over here and talk about that. On the edge of the circle, what is happening? So here, what we calculated is how many radians per second we're sweeping out. But notice that as this dotted line travels from initial to final state, the end of it is traveling along this circle. So if you want to think about it, if you think about a old school record player or a photograph player, or if you want to just think of a bicycle wheel spinning, that's fine too, okay? So if you could visualize the angles, then in radians per second, you can see how fast a bicycle wheel is rotating in terms of its angles per second, radians per second, okay? But if you just fixated your eyes on the edge, on the wheel, then you could say that in the same amount of time that we went from state 1 to state 2, the tip of the wheel, the very edge of the wheel, along the edge, traveled some arc length along its path, the curved path on the edge of the circle per second. That is basically going to be called the rotational speed of a particle on the edge of the circle. So you can think of a record player with a spinning phonograph record like this. How many meters per second, no, we're not talking about angles anymore, how many meters does a particle on the very edge of the circle travel per second? Or on a bicycle tire, how many meters per second? So we're no longer talking about angles, we're talking about linear distance. The problem is because the wheel is curved, it's a meters per second measurement, but it's along the curved edge of the tire. All right, so on the edge of the circle, all right, we travel, and when I say we, I mean a particle travel. We travel a length which is a distance in meters of the following, right? What is the formula for the arc length? We learned that in the last lesson. S is equal to r theta, but since we're basically saying it starts from here to here, and we're really calling this this angle here delta theta. That's what we're really calling it. We'll just call it delta theta, which is just r times the angle in radians that it sweeps out. All right. So the speed on the edge is the following. What is any velocity? Distance divided by time, right? If I travel 5 meters, straight line distance 5 meters in 10 seconds, it's distance divided by time. Any velocity in meters per second is just distance divided by time. We're just saying that the particle is sweeping out along the edge of a circle, a curved distance that we call the arc length. But still, it's distance divided by time. But the distance along the edge is just the arc length divided by however many seconds it took to it took to actually sweep that out. But we already know what the arc length is. It's r times delta t. So we'll just replace this. We'll go and we'll put this in here, right here. We'll say r delta theta divided by t. All right? And then what we can do is say, well, wait a minute. We already know that omega, the angular speed, is equal to delta theta over t, which is the angular rotational speed, angle divided by time. But we have that right here. So we could say it's r times omega. So what I'm going to do is I'm going to circle this. I really wish I had used a different color. Sorry about that. I guess what I'll do is take this away and put a little arrow right here and just make it a little bit cleaner. So we have transitioned from learning what an angular speed is, how many radians per second something is rotating, to trying to calculate the velocity of a particle on the edge of a circle. Right? So all you do is you say, how far does the particle on the edge of the circle travel? That's the arc length traveled divided by the time in seconds. This is meters per second. That's the unit that you would get here, right? So this is meters per second is the answer you would get here. But we already know how to calculate the arc length. It's the radius of the circle times however many degrees you rotate through. So we just substitute that in. So you can use this equation if you want. But then we realize that this quantity, theta divided by t, or delta theta divided by t, is radians per second, which we called omega before. So you could say that the speed of the particle on the edge is the arc length divided by the time. That's fine. Or you could say it's the radius of the circle multiplied by the angular frequency, right? So you can, many times in math and science and physics, there's different ways of solving a problem. If you're given the arc length, then you can easily calculate it, and you know how long it happens in seconds, then just use this equation to tell you how fast a particle on the edge of the circle is traveling. But if instead you're given the rotational, the angular frequency in radians per second, and you're given the radius of the circle, this would make a lot more sense to use because you're already given that information. So it's not so much that this is better than this, or this is better than this, or this is better than this. They're all equivalent. That's why there's equal signs in there. And it's just going to depend on what problem that you have here. So this thing over here was called angular speed. This thing is called rotational speed. Basically, it's the speed that a particle is traveling along the edge of a rotating circle in meters per second traveled around the rim of that circle. This is more of an angular measure. Now, here's a dirty little secret. In some problems, when you're given exactly what you need, you'll just use these equations. That's why I'm deriving them for you and trying to tell you what they are. However, a lot of times when you're actually solving problems, you don't really need to use these equations too much. I went through the exercise of deriving it for you so that we could kind of get comfortable with it. But really, when we solve a lot of problems, you can a lot of times forego using these equations as long as you know what you're doing. So what I'm going to do when we solve the problem, at least the first one, is I'll solve it two ways and show you kind of what's going on. So let's take a look at problem number 1. It says a wheel with a diameter of 50 centimeters makes 1 revolution every 2 minutes. What is the speed on the edge of the wheel in centimeters per minute? So that's the crux of the question. They even give us the units here. What is the speed on the edge of the wheel? So that's not an angular speed. They want to know how many meters per second the edge of this wheel is traveling, but it's not meters per second. They actually tell us they want it in centimeters per minute, but still, it's a distance per unit time on the edge of the wheel. So to start out, it's going to be much easier, as always, to just draw a picture, and we always need a circle for motion involving a circle, so we'll just draw it there. Now it says a wheel with a diameter of 50 centimeters. So that means that this is 50 centimeters, like this. And that means that the radius, which we know we're going to need, is going to go to here, and that radius is 25 centimeters. And that's just the diameter divided by 2. Now, what we're asking in this problem is if you had a particle here and this thing is rotating, which it is rotating, it's going around and around and around, this thing is traveling a curved path. So at any instant of time, its velocity is kind of tangent to the circle. We want to know what is this velocity in centimeters per second of a particle traveling along the edge of the circle. All right, so there's a couple of different ways you can proceed. What I want to show you is the power of unit conversions. A lot of times you can solve a lot of unit conversions without even knowing any equations at all. Let's read the problem one last time. A wheel with a diameter of 50 centimeters, we got that, makes 1 revolution every 2 minutes. What is the speed on the edge of the wheel in centimeters per minute? So let's pretend we don't know any of these equations that I've already derived in the previous boards, and let's just say we don't even know them. Let's just proceed. This wheel is rotating 1 revolution every 2 minutes. So what we do is we set this up as a conversion factor, 1 revolution per 2 minutes. And we draw our conversion bar like this. This is perfectly fine to do. You can set up any equivalence in a conversion factor like this. You know that there are, 1 dozen is equal to, 12 of something. That's a conversion factor. You know that there are 1,000 meters in a kilometer. That's a conversion factor. You know that there are 2 pi radians in 1 revolution of a circle. You could write that as a conversion factor. Any 2 things that are equivalent, even if they're not like standard units that you are thinking about, like liters and things, if they're equivalent to each other, you can always write them in a conversion factor. So we don't typically think of the word rev to be a unit, but it is a unit. A revolution is just the idea of going all the way around 1 time. So even though it's not a typical unit that you think of with unit conversions, it is perfectly legal to put in here because we know that the quantity 1 revolution is equal to the time of 2 minutes. 1 revolution per minute, just like you could put meters per second here. All right? Now we have an important part of the problem finished, believe it or not. All right, then it says, what is the speed on the edge of the wheel in centimeters per minute? So all you want to do is you want to figure out how to get from this unit right here into, and I already made a mistake, centimeters per second. We don't want centimeters per second. We want centimeters per minute. Sorry about that. So we want centimeters per minute. And all we have to do is multiply or divide to get to centimeters per minute. Now look at this. We already have minutes on the bottom. So actually half of the unit is already done. We already have minutes on the bottom. The problem is the revolutions. We want to figure out a way to change revolutions into centimeters. Revolutions into centimeters. How do we do revolutions into centimeters? Well, we already have an arc length formula. S is equal to R times theta. And we can say, well, let's take a look at 1 revolution around this circle, right? How far would it be for 1 revolution to go around the circle? What would the arc length be? The arc length would be the radius, which is 25, which is in centimeters. And for 1 entire revolution, it would be going all the way around, which would be 2 pi radians. So we put a distance unit in here for radius, and we put an angle in here for radians. So this is centimeters right here, and this is radians right here. So 25 times 2 is 50, but then we still have to multiply by pi. What unit are we going to have here? This is centimeters, right? Because this is essentially the arc length going all the way around. Now, what's another way to figure out the circumference of a circle? That's what you're calculating, 2 pi r. All we've done is multiply 2 times pi times r. So I called it arc length all the way around, but it's exactly the same thing as finding the circumference of that circle. And what we have figured out is that the circumference of the circle is 50 pi centimeters. Another way of saying that is we've made the equivalence that 1 revolution of the circle is equal in distance to 50 pi centimeters. This is another conversion factor. When we calculate the circumference around the circle, without saying it, what we're implying is that what we're saying is 1 revolution around the circle is equal to whatever the distance is. And it's an equivalence. It's a conversion factor. Just like 1 revolution takes 2 minutes, we're saying now 1 revolution is also this unit of distance. So what we can do is we can write it like that. We can put 1 rev on the bottom, and we can put the 50 pi centimeters on the top. Why did we write it like this? Because this should be, say, rev, sorry. Rev will cancel with rev, which is what we always do when we set up unit conversions. And we have a centimeter on top and a minute on the bottom. This is the unit we want. So you see, we didn't actually use any of the equations. All we did was start what we know and say, what unit do we want to get? How do we get there logically? Using valid conversion factors. So what we do is then we say 1 times 50 pi is 50 pi. So what you're going to get is 50 pi divided by 2, which is 25. So you have 25 pi, and the unit centimeter per minute. Centimeter per minute. And you can approximate this, or when you take 25 divided by, multiply by 3.14, 78.5 centimeter per minute. Now this is the answer to the problem. Now this is not probably the way most people would think to solve this problem, to be honest with you, because I just gave you all these equations. We didn't really use them, right? But you actually did use them. It's just that we did it in a totally different way. This is extremely powerful. You didn't even know what the equations were. You just knew what unit you were trying to get to. And of course you knew the arc length to tell you the circumference all the way around. And that's how we did it. Now let's go back and try to solve it a second way using the equations that we actually have. All right, so what this problem asks for is what is the velocity of a particle on the edge of the circle in centimeters per minute? And we actually have an equation for that. It's some arc length multiplied by time, or divided by time, which is this over this, which is also the radius of the circle times omega. So let's just use that. V is equal to r omega. So we could blindly say the velocity on the edge of the circle is equal to the radius of the circle times the angular speed that the circle is rotating at. This is going to convert it into meters per second. So what's the radius of this circle? Well, the radius is given to us as 25 centimeters. So I'll put 25 right here, right? And what is omega? Omega is in radians per second. Now that's the trick. I don't actually have that for this problem. But I do know that I can go down here and say that I'm traveling 1 rev every 2 minutes. 1 rev, or 1 revolution every 2 minutes. But I also know that I know that 1 revolution is exactly the same as 2 pi radians. Why am I bringing radians into it? Because in order to use this equation, I need some radians per unit time, in this case, radians per minute. So what I'll do is I'll cancel the revs, and what I'm going to get here is 2 pi on the top, but I'm going to be dividing by 2 on the bottom, and the unit is going to be radians per minute. And when you cancel the 2's, it's just going to be pi radians per minute. So what we have figured out, because this is a unit of angular speed. Angular speed is pi radians per minute. So every single minute that goes by, we travel a half circle, because pi radians is halfway around the circle. 2 pi radians is around the whole circle. So every half minute, it goes another half of a circle. That's telling you how fast in terms of angle the thing is rotating. So if you now know omega, which is radians per minute, and you know the radius, which is in the same the same unit of time, which is in this case, or in the same unit of distance that you want in terms of centimeters, then we'll put pi in here. So 25 times pi, and then what you're going to get is, because you have centimeters here and you have minutes over there, it's centimeters per minute. So this is the way I think most books would probably want you to solve it in the beginning, right? You would say, I want the velocity on the edge of the circle. I can use any of these. I'm going to say it's the radius times the angular speed. The radius is given to me. All I got to do is find the angular speed. But I'm given the angular speed in a different unit, revolutions per minute. I convert it to radians per minute by getting rid of the revolutions, by knowing that 1 revolution is equal to 2 pi radians. Some sort of way you have to know what these units are. That's why I'm kind of going over it again and again. So you know the angular speed is radians per, either radians per second or radians per minute, whatever you're working at. In this case, we wanted to keep it in minutes because the problem wanted the final units to be in terms of minutes for that speed there, centimeters per minute. So I convert it to radians per minute. This is omega. And then when you take omega times the radius, you get exactly the same answer as we got before, where we really didn't even know what equation we were using. We're just trying to convert units to the correct place. All right, let's take a look at our last problem. A disk has a diameter of 12 centimeters and rotates at 45 revolutions per minute. How far will a point on the edge of the disk travel in 1 minute? So it's kind of asking you sort of the velocity, but really it's more asking you the distance a point on the edge of a circle travels in 1 minute. So what we want to do is take our baseline to be 1 minute and see what happens along the edge of the circle, all right? So as always, first we're going to draw a picture. So here is our circle like this, and let's draw what we know. So it says right here that the diameter is 12 centimeters. So that's the diameter. And so if this is the diameter, then the radius right here is 6 centimeters, like this. All right, and then the other thing it's telling us, it rotates at 45 revolutions per minute. So I'll just draw a little arrow right here, 45 rev per minute. Rev per minute, okay? And then how far will a point travel in 1 minute? So basically when we start here and 1 minute later and it moves, how far does it move? So what you're really asking is how far along the arc does the thing travel in 1 minute? All right, so again, let's dispense and not even use the equations. Let's just write down what we know. All right, what we know is that we start off with 45 rev per minute, and that's a valid unit. 45 revolutions in 1 minute. Now, this is a little bit silly, but the problem is asking us what happens after 1 minute. So we know it's 45 revolutions per minute. How many revolutions does the thing travel in 1 minute? Well, we're just going to multiply by 1. So if it's 45 RPM and you travel over a 1 minute period, these cancel, and so it's 45 revolutions. 45 revolutions happen in 1 minute. All right. Now, we want to figure out what is going on over 1 revolution. So for every 1 revolution that happens, because notice there's 45 revolutions that actually happen over a 1 minute period. But for every 1 of these revolutions, we know S is our theta. And so the arc length that's traveling over a 1 revolution period is just going to be 6. And what is theta going to be? Over 1 revolution is going to be 2 pi radians. So what we get is 12 pi, and what's the unit of arc length? It's in centimeters because this was in centimeters here. So centimeters for every 1 rev. So what have we figured out? What we figured out is this thing is rotating. Every single time it rotates, it goes all the way back to its starting point. Then because of the radius and the angle that it rotates through all the way around, it travels this distance of centimeters every time it rotates. But then we figured out that in a 1 minute period, it actually rotates 45 times. So the question says, how far will a point on the edge of the circle travel in 1 minute? We know how many revolutions the thing happens in 1 minute, and we now know how far every one of those revolutions actually is. So we have to multiply those two numbers together. So 45 revolutions happen altogether, and then multiply by 12 pi centimeters for every one of those revolutions. And so what you get is 540 pi, which is approximately equal to 1695.6, which is approximately equal to, with rounding, 1700. And that's going to be in centimeters. Why? Because this is a unit of centimeters. The arc length is a unit of centimeters, and we do it 45 times, so the total unit is in centimeters. Distance traveled in 1 minute. So it was kind of a two-part problem. The first part of the problem is we're told how fast this thing is rotating in terms of revolutions per minute, right? So we have to figure out over a 1 minute period, how many times does it rotate? Well, it's kind of given to you in the problem, 45 times it rotates in 1 minute. And then we just calculate how far around does it go every time it goes. Now I used arc length, but don't forget, this is just the circumference of a circle, 2 pi r. So this is the distance the thing travels over 1 revolution. So 45 rotations times every revolution tells us how far this thing traveled altogether. Now I'm not going to lie to you, the first time I learned about angular speed and rotational speed, it was a little confusing keeping it straight. The only way you can get over that is by understanding the units and applying these to actual problems. So you have to get over the fear that you have initially of what is an angular speed. You have to get over that. You have to understand what radians are and realize that an angular speed is just radians per second or radians per minute or radians per hour, some angle per unit time. But separate from that, along the edge of the circle, a particle is traveling some linear distance over some time period. So it's going to travel some number of meters, which is along the curved arc length there. But we can mash together these two ideas by understanding that the distance traveled on the arc length per unit time can be converted and get the same exact answer in meters per second as by knowing its angular rotational rate along with the radius of the circle. And you can see that if you have the same rotational rate, like let's say it's 10 radians per second, and you make a bigger and bigger and bigger circle, the velocity has to be bigger. Because if you have a small circle rotating once, 2 pi radians, and a gigantic circle rotating once, the big circle has, a particle on the edge has to travel much farther to go all the way around. So if you have the same angular speed with a bigger circle, the velocity on the edge of the circle for a bigger circle has to be much higher, right? When you look at a record player spinning near the center and you actually follow it with your eyes, it's not moving so fast, but on the edge it's moving really fast because it has to travel a farther distance in the same amount of time as all the particles near the center, right? All right, so what we have to do now is I need you to practice these problems and then follow me on to the next lesson. We'll wrap up the concept of angular speed and rotational speed.